So welcome back. So our last speaker is Xinyuan Zhao from Beijing University of Technology. She's going to talk about HPR-LP, an implementation of an HPR method for solving linear programming. So let's welcome.
Okay. Hello, everyone. First of all, I will thank the organizer to invite me to be here and give me a chance to show our research work about an efficient GPU-based method to solve a very large linear programming. This is the joint work with the research group at the the Hong Kong Polytech University, Chair Professor De Fengshun and Assistant Professor Yanchen Yuan, and two PhD students, Kai Huangchen and Guojun Zhang. Okay. Here is my outline. First, I will introduce the linear programming and its due form. And next, I will start with the accelerate preconditional ADMM method for the convex optimization problem. Here, ADM is the alternating direction method for multipliers. Then I will apply this idea to solve the very large linear programming. We develop a very efficient method, Happen-Pisman-Richardford method. Then I will report the numeric result, which compile with the exist state of a exist solver. Okay, and last I will give a summary. So if you're familiar with the optimization, or if you never learn something about optimization, here we give a brief introduce about the linear model, linear programming model, and its due form. For the linear programming, we have the linear function in objective function, and we have the linear equality and inequality constraint. And here X in the set which has up bound and lower bound. And this one is the corresponding its due problem. And for the I combine this the matrix A and A1 and A2 in the matrix A. And here the Y we have two parts. One is in the whole set, the other is in the first order. For this problem, we have a lot of application. For example, we have the production plane problem and the data center resource allocation problems, and the logistic and the transportation problem. Finally, in the financial investment problem, all this problem is related to the LP problem. Okay, and we know for example, for this data center resource, nowadays the cloud providers try to reasonable allocate their limited resource to satisfy some demands or improve resource utilization efficiently. It can use LP to solve this problem. But the scale of the problem is very large. So the question is, has the LP problem already been solved? We know this problem, LP, is the classic optimization problem. And in 1947, George Dancy, he introduced the simplex method. Okay. And in 1979, Hachiya introduced the ellipsoid algorithm for solving LP in polynomial time. Particularly in 1987, the Kamak's interior point It's opened a new era for solving large-scale LP problem. And nowadays, the splitting algorithm also apply to divide a large-scale LP problem into small sub-problems for partitions, constraints of variables. So for nowadays, the LP solver, we have commercial solvers such as Groovy, Simplex, Mosaic, and COP. This is from our Chinese company, and the ManOp is from Ali company, and Opverse is from Huawei, and also have open source solvers. The first one is SIMP, which from the Zui Institute, German, and GLOB is from Google Research, and the Jump Map, this is from the Julia Group, okay. And the CLP is from Lehigh University. So you can see there still are very hot topics in our optimization area. The problem is the challenge of solving large-scale LP problem is how as problem size increase to million or billions of the variables and the constraints. This solve face growing the computational challenges. For example, the first one is storage limitations. Okay, when the large scale LP problem, which we want to allocate in the computer, we need more memories. Okay, so it's a big issue for solving this large scale LP problem, particularly for the embedding system or mobile system. And the second one is computational capacity. Okay. As LP problem goes large, solving them take insensitively sometimes becomes impractical. You cannot have enough time to find the solution. The last one is solution efficiently. We know we have CPU. Okay, we can use the parallel technique. But for the new hardware, such as GPU, the different structure in the hardware. So how to develop an efficient method for GPUs? Okay. So recent research progress, we have some we call the first order method, which is very popular in machine learning, or we call it matrix-free method. Okay, the typical is SCS, which is based on operator splitting or ADMM method, developed by Stanford University group, and ABIP is ADM-based interior point method, which developed by the Xinyuan group. Okay. I think he is one professor, honor professor of our center. Okay. And the Singapore, which is an inexact proximal augmented Lagrange method, which developed by the NUS group and the Professor Taoqing Chen and Defeng Sun and Xu Dong. Okay. The fourth one is Nesterov accelerated gradient method. Okay. And the last one is PDLP, which we call is prime dual hybrid gradient method. This is developed by Google Research. Okay. And this solver is win the RSMP, I think maybe 2 years ago, the winner. Okay. So this solver is more efficient than SCS or other method. In their paper, they report the numerical results of this one, of the test problem. Okay. So what we will do for ourselves. We try to solve linear LP problem, and we have a lot of existing solvers, which is matrix free. So how should we do? So our idea is we start from the more general framework, convex optimization. We design an accelerated preconditional ADM to solve the convex problem. Okay. So this is a general form for a convex optimization problem. And this one is the corresponding dual problem. We look at the convex problem. For this problem, we have a spatial structure. In the objective function part, we have two separable functions, f1 and f2. And in the constraint part, we also have two parts. One is about y, the other is about z. So it's also separable. This is a typical case for the using splitting method. Okay. So we try to use the idea of splitting method, but the object function, because we have the constraint, so we try to use augmented Lagrange method, the idea of framework, to solve this constraint problem. Okay, we penalize the constraint in the Lagrange function. We call the augmented Lagrange function. And here sigma is the parameter, penalty parameter. Okay. So we try to minimize this augmented Lagrange function. Okay. To ensure our problem is well defined, we need one assumption is we need to add two process items. These two T1 and T2 to be two self-adjoint positive semi-definite linear operator on the space Y and Z respectively, such that these two sums are positive definite. Okay. So that under the assumption 1, each step of the preconditional ADMM is well defined. Okay. Then under this assumption 1, we have the following algorithm. A preconditional ADMM for convex optimization problem. You can see I have three variables. Y, Z, this two variable is for the prime problem, and X is in the dual form. So I solve these three variables together. Okay, but I first solve the fix Y and X, solve Z. Then I update the multiply X, then solve the fix Z and X. Okay, then I solve Y. So we splitting the variable Y and Z respectively. Okay. Then to try to get a large step, I use relax strategy. I use a parameter rho to get a large step. Here you can see the rho belongs between 0 and 2. Normally, if rho equals 2, is a semi-proximal Pitman-Richeford PR algorithm, but this algorithm may not converge. Okay. So what should we do? Because the algorithm we cannot prove is converge, it may be unstable. Okay. So we try to get more efficient algorithm. Okay. So I will show the existing capacity result of ADMM type algorithm. And here we have 3 kinds of ADMM. And the dual step size, this two is 1, and this one is a large step size. Okay. And for the first one, the capacity is about 1 big O 1 over K. Okay. But this one is agogic. Okay. This is for agogic case. But for the last two column is non-agogic. The capacity only is small o 1 over square root k. K is the iteration number. So the question is, since for agogic case, we can get a better capacity, the KKT ratio of PADMM converge at most is big O or small o 1 over square root k. So how can PADMM be accelerated to achieve a rate of big O 1 over k or better? So we try to answer this question. So the whole roadmap is we try to find a technique to accelerate the precondition ADM method. So we try to get this accelerated PADMM. But how? We explored the link between the preconditional ADMM and the degenerate proximal point method. Okay. Usually we know the PPA method. Okay. But for us, it's degenerate case. I will explain the detail. Then why we try to solve this one? Find this equivalence allows us to use the fixed point theory to accelerate the degenerate proximal point method. So we can embed in the hairpin iteration to accelerate this DPPM. Then we prove these two methods is equivalent. So we can accelerate the original preconditional ADMM. This is the first time we find the accelerate strategy for the ADMM method. Okay. So the key is how to prove this one is a fixed point method, because this one is degenerate. So first, I need some condition or some definition. The first one is the KKT system for the convex optimization problem. This is the dual feasibility. And we have these two. It belongs to the subgradient or subdifferential of the two operator F1 and F2. This is the set value function. And this KKT system is equivalent to the monotone inclusion problem. This one is we try to find the solution W such that this one is the solution of the general equations. Okay. And to have the solution, we need the second assumption is the KKT system has a non-empty solution set. Okay. It's a very natural assumption. Okay, now we can introduce the degenerate proximal point method. For the classic PPA or proximal point method, we have this T maximum monotone operator T, and with the this term is a proximum term. And the classic scheme, this matrix M or the operator M is positive semi-definite, positive definite. Okay. So, but for us, for our case, this M is positive semi-definite. Then for this one, we already know it can be written as a fixed point method when M is positive definite. But how about when M is degenerate case? Okay. Then we use the relaxed step to get a big step size. In 2022, okay, we have a new concept. Is an admissible preconditional M is for the operator T. Okay. This T is here. It's a linear bounded self-adjoint and positive semi-definite operator such that the T hat defined is the inverse of the sum of M and plus the T times M. This one is this T hat operator is single value and full domain. Okay, which means the existence of this inverse, even when M is positive semi-definite. Okay. So use the admissible preconditional, this constant. Okay. We can, for the linear operator M, this is for the proximum terms. The structure, the matrix is defined in this form. Okay. Here, T1 and T2 is the proximum operator, can be 0. If T2 is 0, we have 0 row and column. So M must be degenerate. Okay. So we have the proposition 2.1. If start from the same starting point, W0, the sequence generated by the PADMM method and the degenerate PPM method is identical. Okay. Moreover, M is an admissible preconditional, and the inverse of M plus T is Lipschitz continuous. Okay. So use this proposition, we can have a convergent method. Okay. We define the operator F hat rho, this one. We prove this operator is M non-expansive, which are similar to the non-expansive operator. This is for the fixed point theory. But here we should pay attention to this M. M is positive semi-definite, which means the norm here is semi-norm. Okay. So after defining this operator, we can have proof the accelerated degenerate PPM is equivalent to a fixed point method with the operator F hat rho. Okay. So of course, we can use the accelerate technique for the fixed point method. Okay. So we choose happens iteration, which is combine the starting point and the current fixed point with these two scalars, a convex combination. This is an accelerated degenerate PPM method. Okay. So we prove under the assumption 2, and M is admissible preconditional. We have the sequence generated by degenerate ppm is convergent to optimal point. Okay. And the second, the capacity of the algorithm 2 is big O 1 over K. Okay. And this one is the KKT residue. It's different from other method, which maybe is prime infeasibility or dual infeasibility. We'll use the KKT residue. Okay, if without acceleration, the degenerate ppm, when rho equals 1, we have big O1 over square root k, the iteration capacity. Okay. Now we move on to LP case. The linear programming is a special case for the convex composite problem. So we can use the idea for the convex programming. We call the method is Happen-Piezman-Rutherford method. Why we consider for the LP is have the different structure for the general case, the convex optimization problem. The difference is here. In convex case, we have B1, B2, 2 matrix or operator. But for the linear LP, linear programming, the coefficient before Z is identity matrix. Okay. So for this one, this spatial structure, we can choose the proximate item response to Z is T2 to be 0. And we choose T1, which is corresponding to the variable Y, such that this sum to be positive definite. Okay. And this is our augmented Lagrangian function for the dual of LP. Okay, so for HPR method with semi-proximal terms for LP, why we call this one is semi-proximal? For the variable Z, this proximal item is dismissed. And we choose the relax factor rho to be 2, which is the largest one. Okay. If you choose 2.1 or 2.09 or 0.1, the sequence may be not convergent. Okay. The 2 is the largest one. Then we use the happen iteration. But we know even we use relax step or happen iteration, because this kind of method is first order method, it may not be decay efficiently. So how to improve this one? Okay, first I will introduce the complexity result of the HPR method. Okay, if the assumption 2 is holds, then the sequence generated by the HPR method will satisfy this inequality. This is prime infeasibility, complementarity, and dual infeasibility. This means this is the KKT system or KKT residue. And also we have the gap, the dual objective function error. Okay. Both the capacity are big O 1 over K. So the final I give the efficient HPR-LP method with restart technique. Okay. The out loop is we use the HPR scheme here, but we need to use the restart for the T loop. Okay. So when you solve or update your variable W bar, then we do the relax step. This is a happen step. So if one of the restart stage criteria or all the termination criteria are met, then we output. Otherwise, we need restart. And if all the termination criteria are met for the out loop, we finish our algorithm. Otherwise, we need update the parameter sigma. This is a penalty parameter. So there is two parameters in this algorithm which will affect the convergence or the speed of the algorithm. One is when we should use restart. The other is how to update the penalty parameter sigma. This is two difficulties. So we base on the proposition 2.2, we get the restart strategy. But here in the proposition, we use the optimal solution, W star, okay. So for the practice case, we need approximate by the current point, which is W head RT plus 1. So, and this ratio or arrow, we can get the restart strategy for the HPR-LP. If our algorithm is sufficient decay, if satisfy this condition, we need restart. And if it has some decay, but no local progress of this arrow, which means we satisfy this condition, we need restart. The last one is the worst case. We have long inner loop, which means our the number of iteration is achieve our maximum value. Okay, so we need restart. And how to adjust this restart strategy? We have three parameters: alpha 1, alpha 2, alpha 3. The alpha 1 is between 0 and alpha 2. Alpha 2 is between 0 and 1. Alpha 3 also the same. Okay. In our algorithm, we choose alpha 1 is 0.2. Alpha 2 is 0.6. Alpha 3 is 0.2. Okay. And the next one is update rule of sigma. This is very important for augmented method because this one will affect the speed of the convergence. So we construct an optimal problem. We try to solve this one, get an explicit solution. Okay. So we can use this solution to update or approximate the penalty parameter sigma. Okay, it's very efficient in our algorithm. These two stages is the key point for speed up our algorithm. And also we have one interest item is the proximal point item. In our sub-problem, we need to solve linear system. But we know we can solve by direct method, such as LD-LT method, or we can use Cholesky factorization, but both are too slow. We use the proximal item with spatial choice. We choose lambda identity times identity minus A times A adjoint, which means for our linear system, we only have diagonal matrix of the coefficient matrix. Okay, so we can solve this one by one. We don't need to compute the inverse or do some factorization. And based on this choice, our sigma have a simple form. Okay. If LP with spatial structure, such as OT problem, T1, the operator T1 can be 0. This sigma can be more simple. Okay. So this is also although we have not very exact solution, we get an inexact solution, we still can faster and achieve the optimal solution. Okay, now we can look at the numerical results. First, I will introduce the computing environments. Our HPR-LP is implemented using the Julia language. And the PDLP we use is Julia version. And we use the GPU is NVIDIA A100 with 18 gigabytes GPU. Okay, CUDA is 12.3. And for test compare with Groovy, we only have the CPU version. Okay, so we work on this workstation with 256 gigabytes memory. And for all the methods, we have the same termination criteria. We use the dual gap, the relative dual gap, relative prime, and dual infeasibility. And how to compute the time, we use the shift geometric mean of solving time. We use sigma 10. First, I will show the efficiency of the restart strategy. We consider for NAC 08 the instance, which with the Groovy to resolve. For this problem, the LP problem, it have 20,000 variables, about 20,000 constraints. Okay. And then the non-zero elements is about 39 minions. The first, we apply the PR Pitman-Richford method. Then we use happen iteration to accelerate the PR method. You can see this one is better. For the PR, is about the accuracy is about 0.1. And for HPR, it's about 10 power minus 2. Then we use HPR with restart. And for the penalty parameter sigma is fixed. We have this strictly decay. But if the sigma is automatic, update. Okay, so it can adaptively. So the HPR restart is more faster. So you can see the restart and the sigma is very important for the algorithm. Then we try some benchmark to test our algorithm. The first one is Xinyuan-LP benchmark with presolved case. We can see we compare with the PD-LP. Okay, so we can solve maybe 3 or 5 more problems than PD-LP. For the speed up, maybe more than 3 times than PD-LP. Okay. And for without presolved, we have different accuracy. So here I need to mention all the methods are first order method. We still can achieve the high accuracy is 10 power minus 8. Okay. So also we much faster than PD-LP with the speed up factor more than 2. Okay. Then we also test the mixed integer problem. This is the relaxation of the mixed integer problem. This one, the scale is much large. Okay. So we can solve for the accuracy is 10 minus 8. We can solve 7 more problems than PD-LP. And the speed is around 2 times. Okay. And this is without, also the same. And for the QAP, quadratic assigned problem, this is from the combinatorial optimization. And for the LP relaxation of QAP, this problem is a large-scale LP problem. You can see with resolve, our method is much faster than PD-LP. It's more than 4 times speed up. And for the without resolve, is more than 2 times than PD-LP. Okay, we consider a much larger case is ZRB problem. This problem is about, we have about 20 linear rows and 30 linear columns. This is non-zero element for the constraints. Okay. So this one is much larger. And for the QOP, it will use 16.5 hours to solve this problem. But for us, with resolve, okay, we need more than 3,000 seconds. And for without resolve, we need 4,000 seconds, which is speed up about 4 times than PD-LP. It's much faster than this one. Okay, even for CPU case, we compare with Groovy with 32 threads. We test Bitmain's LP benchmark instance with resolve. And the tolerance is 10 minus 8. And we set the time limit is 15,000 seconds. And you can see this is the scale of the problem, LP problem, and this is non-zero element. And this is our method. Okay, we can solve very fast. This is the barrier method in Groovy, which is interior point method. For this one, it's out of memory. And for the prime dual simplex method, you can see for this case, it's reach the time limit. Okay. And for this one can be solved in more than 7,000 seconds. It's much slower than our method. So finally, I give a conclusion. We propose an accelerate degenerate proximal point method with big O1/k iteration capacity. Use the happen iteration. Based on the equivalence between PADMM and DPPM, we drive an accelerate PADMM with a big O1/k iteration capacity for the KT residue and the objective error. We introduce the happen HPR-LP, an implementation of an HPR method for solving a larger scale LP problem. And in the sigma 10, the HPR-LP is achieved more than, from 2 times to 5, more than 5 times speed up with pre-resolve. This is without pre-resolve case. Over the PDLP, the tolerance is 10 power minus 8. So we can see we introduce a first order method with a high tolerance in very fast few seconds to solve the large scale LP problem. And the last page, we announce our package in GitHub. Welcome all of you to test it. Thank you.
Yeah, thanks for such a nice talk. Any questions?
I have two questions. And 3 questions and 2 comments. The first one is I didn't understand what K is. Can you please explain more about
it's
K?
The iteration number.
Iteration number.
Yeah.
It's normally we use the columns number and the variables number or something like that.
No, this is for the complexity of the algorithm.
Complexity of the algorithm.
Yeah.
For example, for any LP, we use in the computational complexity, we normally use how many rows in the constraints, how many columns, and how many variables. We never use the iteration number as K. Say use that one to compute the complexity, as best of my memory. But for example, simplex.
Yeah.
Simplex is MN. M is the columns number, and N is
the number of variables.
Yeah, variables, something like that. Can you explain a little bit between K and MN?
Totally different. In optimization, MN is show the scale or the size of the problem. Yeah. For the K is the number of this one. I don't have this one. Okay. This one is
iteration. I understand. Okay, you can set up a K number, right?
Yeah, which means maybe we need about some scalar times K steps. We can find the optimal solution.
So that will come to my next question. Say I'm just wondering how can you guarantee the convergence? You guarantee you algorithm can be converted to optimal solution.
Yeah.
And secondly is I guess you got the approximation solution.
Yeah.
But it's not exactly the accurate solution in LP. So my question comes to 1, converge, and the second, accurate.
Okay. I have two assumptions. First of all, I discuss here is the convex case. So if I found the solution of the KKT system, it must be the optimal solution. Okay, because
But in your numerical case, for example, you have 207, examples. You didn't solve any. You didn't solve the, all of them. So what happened if you claim this one?
Okay. So first, I need the assumption one to ensure our problem is well defined. And second, I need assumption two to ensure I have a solution. Yeah. So the KKT system have the solution. So if, yeah. Then finally in our numeric part, okay, I have the optimality. This is my tolerance. Okay. In numeric case part, we assume if I achieve this tolerance, we get the solution. We stop the algorithm. For us, it's 10 power minus 8.
Okay. Did you try the KL anti-example in the LP? Try some anti-example with the simplex method.
Simplex is much smooth. I compare with simplex method, which is in Ruby. I think Ruby is the here. I compare the simplex method in Ruby with prime and the dual simplex method. You can see it need much more times to solve the large scale LP problem.
Yeah, this is by computer. I mean, we do have LK anti-examples in LP. That's a question you can tell from the hand calculation. Simplex complex. Basically, I suggest you can try to use that examples by using your algorithm to have a test.
Okay.
Yeah. And another question is degradation problem. I mentioned somewhere you say you can do the degradation. Degenerate, yeah.
Okay. Yeah. Degenerate, yes. Yeah, this one. This one is a positive semi-definite. Yeah. So if I choose T2 is 0. This one is degenerate case. We have 0 eigenvalue. And this will bring the difficulty is here. The norm is semi-norm. And we need proof this operator is M non-expansive. This is a key. Yeah.
Thank you. And I finished my question. I do have 2 comments. You can go to the first 1 or 2 slides talking about the square. You do the Lagrange square.
Method.
Yeah, the 1 or 2 very beginning. Yeah, next one. This one. Yeah. Do we happen to try the power 3 as well? I just wonder.
Power 3?
Yeah, so currently you are using the second mode. Yeah, did you ever try the 3?
Yeah, maybe someone tried the high order. Yeah. But
do you think higher will be better?
I'm not sure.
Maybe, yeah, I guess so. Because
maybe not. Because the high order, the convexity is more complicated.
Yeah, so that comes to my second comment. You have a slice show X, Y, Z. You fix one and do the other one.
It's splitting method.
Yeah, this one. This one. Yeah. So did you try change the order? Say you do fix Y first and fix Z first, or fix X first. They might different.
Z and Y can change. The position is the same, but X must be in the middle part. Otherwise, I cannot prove it's equivalent to the degenerate PPM or ADMM.
Currently, you do
this
Z,
way,
X, Y.
This one must be fixed in the middle part, and the Z and Y can change.
Can change. Did you test if you change
the
order?
I test.
What will happen?
The same.
Oh, they're same. Give you the same
almost
result.
The same.
Oh, okay. Interesting. Sometimes if we change the order, maybe because in this case, if we do X, Y, Z at the same time, get the best optimal solution. Or we fix one and do 2, we did get the difference.
Yeah, if you solve Z and Y at the same time, this is augmented method or augmented algorithm, which means you have a large system. If I fix Y to solve Z or the fix Z to solve Y, it's different system. With this splitting is we split the large system to the 2 small case, 2 small subproblems.
Okay, makes sense. Thank you.
Yeah, thank you.
So I wonder, in practice, is simplex method more useful or ADMM is more useful? And in which circumstances can they be applied?
Okay, these are good questions. Because I also do the simplex method. And you can see in my numeric part, I have the benchmark. Okay. You can solve, we can use with pre-solve, and we also have the case without pre-solve. Okay. I think for the super large, I think maybe more than 10 billion. I think simplex method, because we can use the column generation strategy. Okay. And for the other case, this kind of the matrix-free first order method is efficient. Yeah.
Thanks. Any more questions? If not, let's answer then.
Thank you.